All right, so we're going to get back rolling. Okay, so we've kind of gone through a lot of the building methods. Now let's talk a little bit about floors and roofs, and then we'll get into the fact that there's no cavities. So we're again back to the building codes for heavy timber construction if it's going to be only heavy timber construction and you're getting that fire rating, so this is not mixing. If that is the case, then the floors and roofs need to have solid wood construction. So this is where we're talking about that tongue and groove, right? We need solid wood separating the floors, so it's not just plywood, okay? There are no concealed cavities, right? So in platform frame, right, we have our joist running, and there's a concealed cavity. We put drywall on the bottom, we put flooring on the top, right, and we run our insulation and pipes in the middle, okay? Unfortunately in this, right, we have our beams and our girders and then our beams, and then we put this planking or decking down, and then we can put plywood on top of that. So it's a solid wood transition. We can't put any insulation, we can't put any plumbing in there. So here's our variety of types of decking. We have our tongue and groove, and this is an example of tongue and groove. Sometimes it's just one tongue or groove, not the two that are here. Sometimes you have it where you have a groove that runs through the whole piece and you put a spline in, which is just another piece of lumber, right, that goes in the middle. We have glue laminated decking, so this again connects together and we end up with laminated deck, okay? Many times they'll mix the types of building, right, and you'll have light wood frame mixed in and you won't have this, so you have the cavities. So it's less common, but this is for that type of construction, right? So here we are. Okay, we have our girder back here. See how it's much bigger than the beams? Right, that's kind of the key thing to understand. This is a glue lam here. Then we move into our beams here. Right, on top of our beams we have our tongue and groove decking, right, or planking. So it's again solid wood, and then on top of that we have plywood, and then on top of that we have whatever our finished floor is. Right, so it's a pretty big sandwich. Okay, so you can use plywood. Right, you can use other composite materials. So it's not, once you have that solid wood decking, you can do what you want above it. Okay? More common these days is that we're actually going to blend the two styles. And the key thing about blending is as soon as you do, you're back down to the Type 5 light frame fire rating. Okay, so you have to deal with everything. You have to fireproof it, you have to put sheetrock on it, that sort of thing. Okay? So in here, good example, right? This is obviously kind of a half truss, so to speak, right? We have our heavy timber here supporting the roof load, but on top of the heavy timber, right, we have all kinds of engineered lumber. These are our I-joists, right, that are then supporting the roof deck. But this is not, because it has a cavity, that heavy timber Type 4 construction. So if we're in seismic areas, right, we have to handle, how do we deal with this seismic loading? Okay, which we talked a little bit about earlier. So it's not only in the joints, but very often we're going to have some kind of diagonal braces, or we're going to have some kind of shear panels. Okay, and so in this instance we're seeing our big diagonal braces that are helping this building stand up. I'm not quite sure why you need this building to handle an earthquake, because it's pretty shot to begin with, but you at least get the idea. And in a lot of the slides that I've already shown you, there are already diagonal braces that are helping to support. And a lot of slides that I will show you. So the thing about this is if you're working in a solely heavy timber frame construction building, so again we can see right here, there's our plank decking, right, solid wood. This is all heavy timber. Okay, same thing, we've got our decking up here. Okay, there's no cavity to conceal anything. So when we think about the stuff that's running in our walls and our houses, right, we have plumbing. We have electrical. We have our heating and ventilation and air conditioning, right? Our HVAC ducting, okay? We have all this stuff. How about insulation, right? We have insulation in there too. We have all this stuff that we conceal, okay? If we're in this kind of a heavy timber frame building, we have no way of concealing that stuff. So we have to be very careful when we're designing it about how we're going to either expose or somehow hide with false walls or extra construction, whatever these things are. Yeah? Yes and no. It depends on where you make it. Generally, you try to avoid it. So you look up here, right? This is obviously ductwork, so it's bigger, right? And they're running it on the outside, and it's going to end up being exposed. Okay? So a lot of times there isn't a cavity. You can go through it, and you won't damage too much. Primarily, I would say for electricity, because it's not that thick, right? Supply plumbing, sure, that's not that big, but as soon as you get into waste plumbing, you're talking too big, and it's going to compromise the structural integrity of the beam, so you're going to want to find a way around it. Okay? So it's challenging. So then let's move into, we want some long spans, right? We're in wood, but we need to span some distance now. Okay? So we have large beams, which basically are glue lamps. We talked a lot about those already. We have rigid frames. Then we move into trusses, and then we'll have arches and domes. Okay, so we're getting distance out of our spans. Okay, so large beams are extra large glue lamps. So you guys have all seen this. We passed it around, right? This is what we're talking about here. The extra large beam, right? Or girder, so to speak. Right? So these can get up to 72 inches, right? So they can span a long distance because of their depth. Okay, and so you see it here. To me, this is really funny because we have this giant beam, this skinny little column, right? So obviously, this needs some kind of diagonal bracing that they haven't installed yet, but it's about the span in this context. Okay, so we used our glue laminated beams because they're more dimensionally stable. They're not going to twist. They're not going to bow, right? And that's going to give us better results, right, in our final building. We can also get as deep as we want and as long as we want, within some reason. Obviously, if you have an 800-foot beam, it's going to be really hard to get it from the factory to your site, right? So there are some limits to doing it. Doesn't mean it can't be done, but there are limits, okay? And they're going to be made to whatever the exact specifications are. So you're going to order exactly what you want, yeah.
So in this building, they have like the building next door, they have the trusses. Would you use one of those large beams instead of one of those trusses?
You could, right? And it may take less than one of those trusses. Okay, it may not, you might not substitute out the exact same dimensions. Does that make sense? It's probably shallower than one of those trusses. The advantage of the trusses that are in there are that they're lighter, right? So you in order to use those lighter members, you need more depth to be able to do it. So if we were using a heavy timber, it might be a little bit less in depth, but it would probably cost a lot more because it's so much more material. So generally, when you're doing something like this, it's because you want it exposed. You want to see, right? If you're going to try to hide it, you're going to use whatever the cheapest way of doing it, which is probably not this. Okay, this is for exposed because you want to see it. So we talked a lot about rigid frames in steel, right? Remember, I used the transfer station out in Martinez as an example, right? Rigid frame is one piece, kind of like an arch, and another piece, kind of like an arch, that meet in the center. Okay? So you have one rigid frame and another rigid frame, right? They push against each other on the top. They want to thrust out at the bottom, so you need a tie rod that keeps them together. Okay? And you can span a very long distance because you're using the material in a very efficient manner to get that particular shape. In this instance, right, it happens to be a half circle shape, right? So it's more of a dome structure. This, we could repeat this, right, in many more vents going back, right, and it would be a long continuous hall, right? So it's different manners of doing it. The concept is still the same. You need either a buttress at the bottom or a tie rod that ties the two together because of that outward thrust. Okay? Typically, these are glue laminated as well. This looks an awful lot like the Kruk that we talked about in the very beginning, right? It's on a bigger scale, but the same concept. Remember, the Kruk was the tree that had been twisted that we used, right? We went out into the forest, cut it down, used it for a specific purpose. In this context, because it's a glue lamp, we can make it exactly the shape we want, which is really nice. So we don't have to go find a tree that's grown crooked. Okay, so then we move into trusses. And so a lot of the roof trusses that we talk about are in the light wood frame. So when you see I'm trying to think where that is. Maybe I'll find it for next time. I'm not seeing it, but I have an example of it here. When we see trusses going up, say, on a track house, right, where the members are dimensional lumber, 2x4s, 2x6s, that sort of thing, that put together with what are called gang nail plates. Those are not what we're talking about in terms of the heavy timber trusses. Okay, they work just like the light frame construction. We have a repetition of a lot of little ones that work to hold the weight. When we're talking about larger buildings, it's going to be heavy timber, right? That's working together to provide that spanning. Okay, so it's going to be something more along the lines of this. Okay, so what happens is we have the steel plates, right? We talked about the hidden steel plates in something like this, right? You saw the slide a little bit ago. Okay, and we're forming this shape, which is a triangle that's then broken into smaller triangles. Okay, this is the simplest truss that you can get. Okay, so we're talking triangle, right? Broken into other triangles. Let me make sure it matches. Okay, so it's very, very simple, right? You put weight on it. The arrangement of members, because they're all triangular, allow it to support the load. Okay? Typically, when we're doing this wood construction, it ends up being peaked like this, though sometimes they're inverted. Okay? So, you can use sawn laminated and structural composite materials, right, in combination with the steel to make whatever this is. So the point is, you can use engineered lumber products as well as using solid wood products to be able to make whatever these beams are. Now, you wouldn't go to all this effort to make a truss like this if you didn't want it to be seen. Right? This is not the type of building where you put sheetrock here, right, and hide it. Right? The only reason you're doing this because it's high cost, right, high skill, a lot of labor involved. The only reason you're doing this is because you want to show it off. Okay, so that's really important to consider. Okay, if you do it correctly, right, you can get spans of over 100 feet in this. So you can get some pretty good spans out of it, which is nice. Okay, so here's an example, right, and there's a variety of pieces, and so the more you understand about the structural integrity of the truss itself, the more you can substitute which pieces do what. The hard part about it is you have to develop some structural intuition, and because you don't have a structures class yet, you don't necessarily know this, so you just kind of rely on your intuition. Yeah?
That last slide, slide,
Yeah.
the roof joists, are those going to be called purlings? Is that because we're using
Right.
heavy timber?
Right. These are a little thin to technically be called purlins.
Okay.
Usually purlins are going to be a little bit thicker. In this case, my guess is they're blending in some light wood frame construction,
Okay.
much like where we had those IJOs
We're gonna
before.
call that a roof.
Right.
Okay.
It depends, but yes, you're right. I would be comfortable calling that a purlin if it was a little bit thicker.
Because of the, okay.
Because of the orientation, it's running across.
Okay. And then,
Okay.
on the glue lamp, is, the dimensions of those actual? The dimensions,
Yeah.
unlike,
They're nominal.
no,
glue lamp.
they're also no?
They're also nominal because they're made of lumber that is the nominal.
Okay.
Right? So this is made of a 2x6, therefore it's going to be 5.5. Right? Because we're laminating all those 5.5 pieces.
We said they're all conventional, you meant nominal?
Right.
Did
What?
I say that word? Yeah,
Is that in the slide?
you said they were all.
Well, it's dimensional lumber is what's.
Oh,
You-
dimension lumber.
You meant nominal,
Yes.
right?
Yes, when I'm referring to dimensioned lumber, sorry, I should clarify. Thank you guys for bringing this up because sometimes I go off on tangents and I'm not clear. When I'm referring to dimensioned lumber, I'm referring to lumber that is nominal. I know it's a little counterintuitive, but dimensioned lumber refers to things that are referred to like 2x4, 2x6, 2x8. Okay. When I get to timber, right, I'm talking about larger pieces. It was on a slide last week. I can dig it out a little bit later on. But it has to do with referring to the type of material that you're using. So dimensioned lumber is this type of lumber. It's light frame. It's light frame. Timber, right, and that means it's nominal, right? Timber is referring to the big stuff like this because it's bigger, but that still is nominal in size. So it's the same thing, but where timber is just referring to bigger, dimensioned lumber is referring to smaller pieces.
And
Does that
even-
clarify?
Even though glue lamp bigger is still dimension nominal.
Exactly. Exactly. And the reason it's dimension nominal is because we still have the same issue, right? We're made out of the smaller pieces, right? And all our other engineered lumber, right? All of these kinds of things, they mimic this,
Okay.
so we don't end up confusing.
Confusing the two. yeah.
Exactly. So it's always going to end up like that. Yeah.
When you're mixing in light frame or wood like that, that's not necessarily part of the structure, but you more cosmetic for appearance.
Yeah.
Does the fire rating get changed as well?
Yes, the fire rating still gets
Even if
changed
you
now.
just put it in there.
Unless it's, so in this case, it would still, the fire rating would still go down. If you're building a non-bearing interior partition wall that's light frame, it wouldn't change the fire rating. Okay, because the structure itself is all built with the heavy timber. Okay, so you can still get away with some light frame. It's when it's mixed in where this is light frame and you're using sheetrock as the fireproofing, as opposed to having the heavy purlins with the decking on top. That's when it changes. So when it's used structurally.
So to get the 10 foot fire rating, all the framing is done in every timber, and then everything interior.
Can be the light frame, as long as it's not a structural issue. Okay, so as soon as you separate, as soon as you add any kind of a structural piece, then the fire rating goes down.
So partitions can be.
Partitions can be the light wood frame. With, you know, you're still going to put the sheetrock on them, but theoretically in your house, I mean, we're getting a little bit into building codes to some extent, but as soon as you get out of the structural realm and you're inside a house, it's more about you need to have a tight-fitting door between the bathroom and the kitchen. Right? But other than that, if you build your interior walls out of wood, that's fine. Right? And you don't have any fireproofing on it. Right? So you can get away with some stuff once you're inside and it doesn't have to do with the structure of the house. Because it's not going to collapse. Building burns. Now, it's common practice to go ahead and put fireproofing inside a room so you contain the fire within one room as opposed to having it go through the rest of your house. But it's much more lenient once you get to that stage. But if it's anything to do with structure, then it's going to lower your fire rate. Okay, so another example of a truss here. Okay, in this instance, right, you note that we're using steel cables. Okay, and this has to do with how the truss performs. So where pieces are in tension, okay, they're steel. Where they're in compression, right, they're in wood. So it gets a little weird, and you have to kind of imagine pressing down on a particular piece. Okay, so we'll see if I can do it. Right. In this instance, right, in this arrangement, we're pressing down on this piece, which is compressing these, which is pushing these out, which means these two are steel, right? So because these are stretching and that's compressing, so you have to go through each member and kind of intuitively get it, okay? I'm not going to spend a whole bunch of time playing around with it. I'd rather have you just find examples of things that have been done before, and you can mimic those, okay? When you get to your structures class someday, if you take a structures class, you'll have to calculate the load on each one, and is it in tension or is it in compression and all that sort of stuff. Okay? But for now, just look at examples. Okay? Another type of truss here is called a scissor truss. And a scissor truss is like a pair of scissors. Okay? So we have these two pieces that slide past one another with a post in the middle. Right? Notice we have our steel plate again here. Right? And we're bolting these pieces all together. We're bolting these two in. And we end up with something like this. Okay? So inside, we have a little bit, instead of having a piece running all the way across, we have a piece that's raised up. We have a little bit more space. We have a little more vault inside, so it can be architecturally nice. Okay? Again, all of the segments are broken into triangles. So if you have a truss that has a square piece in it, it's not going to work. Right? It has to be in triangles. That's the key to a truss. Okay? And in this particular example, instead of the steel plate being on the inside, we have the steel plate being on the outside. Doesn't really matter. Okay? Again, crane is lifting it into place. Okay, so a king's post truss has one central post that runs down, right, and one tie that goes across. Okay, this is a little off because this should really be at the bottom, but the same concept here. And then it can have these other side pieces. I'll show you some other examples of a king's post here. Right, we have our king's post here. We have our cross member here, and usually there's a little bit of diagonal. Again, this is rough-hewn lumber, right, so it's not as precise. And then we can move on to what's called a hammer beam truss, and this is if we need a longer span. Okay, so we're built out and up with a diagonal, out and up with a diagonal, until we get to the top where we can span across. So this was created when the distance from this to this was too far to have one solid member there. Okay, so we go up as far as we can where we can get a piece long enough, right, and we build our way down the side. So here's a hammer beam, right? So it can be a really attractive truss, right, but we're working our way up till we get to the top and then our way back down. another example of a hammer beam. So a hammer beam doesn't have a continuous bottom cord that runs all the way across. Okay, another example, right, of a hammer beam. Longer span. Westminster Hall, hammer beam, same concept. Okay, so you can get a really long span out of something like that. Recognize it takes a lot of height to get there too, which can be really nice architecturally to have that extra height. Okay, so sometimes you get really weird stuff. This is the Traversina footbridge in Switzerland. Okay, this is all a wood truss. Certainly they're using steel in some context, right? This is just for people to walk from one side of a canyon to another side of a canyon. Okay, very cool. The Swiss somehow do fun stuff like this, right? So they do something like this. The sad part about this is an avalanche came and knocked it down, so it doesn't still exist. So they built a new one that's out of steel and concrete, so I don't show that example. Okay? But it's very cool. Oh, there it is.
Would they walk on the bottom or on the top?
No, they walk across the top here. So this is where I'm saying, and I made that note right on the assignment itself, you can do the truss either way. The principles are the same. The forces that are acting on it are slightly different internally, which pieces are in compression and which pieces are in tension. But the truss can go below or the truss can go above. Or it can be both. Okay?
Or it could be both?
Yeah, it can go above and below. Depends on what you're trying to do. A bridge is a good example of something that a lot of times goes above and below. Okay? If it's a suspension bridge, that's different. But we're talking a truss bridge. Okay, so arches and domes. So sometimes you need to span even further distances. So this is kind of an extension of the rigid frame method, but it's a little bit more involved. Okay? So you can create a heavy timber vault and a heavy timber dome as long as you can fabricate these really long curving laminated pieces, or you can attach those pieces together in a series of fixed geometrical shapes. Okay? They're often used in athletic arenas or auditoriums, so we're talking big spanning spaces, right? We need a big cavity. And they're very similar to rigid frames. They have to have tie rods or buttresses at the bottom because they exert an outward thrust, right? No surprise, you weight the top, they're going to push out on the side. That's the nature of it, yeah.
So, why don't they use hammer beams instead of...
We're talking a distance that's too far to use a hammer beam truss. It's too much. Right? So when we get to this size, we need something and that the geometry, right? And it has to. You'll see it. Let me switch to the next slide. Okay. So this is the Tacoma Dome in Tacoma, Washington. Okay. So each one of these is a curving glue lamp. Okay. But the two are put together in a triangular shape, right? And so that triangular shape, that network of pieces, allows you to get the span. Okay, and when we get all the way down to the bottom here, we have to have a whole bunch of buttressing support because it's pushing out. So we're using the shape, the overall shape of the dome, right, to transfer the load down to the base, and we're using those glue laminated pieces, right, to carry that load. But we're relying on the buttress at the end, because otherwise it would collapse. Okay, but the point is that you can get a wood frame structure that can be really big, which is kind of fun, yeah.
Sometimes you also want, even if you are able to use the other, the hammerhead, it's because you want the look of the dome instead of the other.
Absolutely, absolutely. From an architectural sense, you're always going to be deciding on the look that you want to. Assuming you can make it structurally work, then it falls to what do you want it to look like.
So probably hammer beam probably get a little more 200 feet.
Yeah, I mean, we're talking in rough numbers. That seems right. 150 feet, something like that, maybe 100 feet. Something like this, we're talking probably 300 feet plus. Okay, so much bigger span. Okay, so here's the general concept here, right? We have our network of pieces that form our arch. Okay, but when we get to the bottom, we need to be able to push into something. So this is that concrete buttress, right? That's all formed up, right? And we have a flexible steel joint that joins together there. All of that load comes down, transfers into the concrete, and eventually into the ground. So that concrete joint isn't allowing this to slide out. Okay, so that's kind of the critical way that this works, which is why we don't need any kind of a tie rod or anything in the middle of it. Okay, so I have a whole bunch of examples that I'm going to show you at the end, and I'm going to try to talk through them. Last year, this slide was the projector sucked and I couldn't actually show this slide. It actually seems pretty clear, so I have two versions of it. I have the black version and the white version. Which version do you guys see better on this? Is the dark one better? So I'll talk on the dark one, okay? So on every one of these slides I have the duplicate. I have the light version and the dark version because I never know what the projector is going to be like. So this is Sea Ranch. Anybody been to Sea Ranch? One, okay. So Sea Ranch was designed in the 60s and 70s by this architecture firm, very well renowned, a lot of whom were professors of architecture. While this will seem very dated to you today, it was fairly cutting edge at the time in terms of using this heavy timber construction to make really neat architectural spaces. So I think it's a good example to kind of go through. So bear in mind that's a little dated, but I think you'll learn something from it. So Sea Ranch is a community of houses that was designed. They're very far up the California coast. So if you get over to the coast, say at like Bodega Bay, you're going to go north maybe 2 hours to get up to Sea Ranch. So it's pretty far north in California, right on the coast. Okay? And so the initial concepts of Sea Ranch were very open floor plans. We're using heavy timber to create these kind of very nice architecturally defined spaces without a lot of interior partition walls. Okay? So we look at something like this and we see the floor plan and it's dominated by the columns. Right? We see the columns placed. Right? And so when we look at the perspective view, we understand that the living area is very open. Right? So at the time, when we rewind ourselves back into the 60s, early 70s, right? We were coming off an era of a lot of houses that were closed in, partitioned rooms, light frame construction, and we're moving in reaction to this and having a very open floor plan, right? So that all the rooms flow together. This is a vacation area. You obviously want to have a place where you can gather with your friends and that sort of thing. That was a lot of the design element. So we're looking at our major columns running all the way up to the roof, right? And they're separating out, so we have this completely open plan here. We have an open plan at the second floor. We have connection between the two spaces. Okay? Some of the early design concept drawings. Oh, sorry. I told you I was going to talk in black, right? Early design concept drawings, understanding how these spaces relate to one another, right? And the fact that the columns define a particular space. So here's a good example. This is the fireplace. The floor above with these four columns defines the area of the hearth, right, such that you can sit in that area. That's designed for the fireplace. These columns define the space. You don't need walls to define the space. So that was kind of the major movement at the time. Switch to black. They were also, the houses were designed as condominiums so that they flow together and they also share central space, right? Again, designed in the vacation community style. This is where it was designed. Okay, fairly picturesque to be on the Northern California coast on these kinds of cliffs, right? Pretty nice place to be. And so they were developed. This is what they look like from the outside. They blend in with the topography of the landscape as a whole. It's considered to be a very famous project in California. Okay, so close enough to where you could actually go visit Sea Ranch. You can rent houses up there and stuff. And so this is what the interior would look like. Again, dominated by the columns, right, defining the particular space of the sitting room. Not walls. Okay? This is the team of architects that did it, most of whom are dead now. Donald Linden, who is here, used to teach at Berkeley. Charles Moore taught at Berkeley. Turnbull, I think this is Turnbull. He's the youngest. He's still alive. But so this was a very famous project at the time. These are some of the early concept sketches and then the photograph of what it was like built. Again, we're using the scissor trusses that we saw before, right, to create these open spaces. So it's nice to see the concept sketches as well. And this is the actual outside of the building. Okay, so let's fast forward, right, to this century, actually to maybe 15, 20 years ago. This is the Scottish Parliament building, okay? This is the truss system that's inside the main debating chamber of the Scottish Parliament, okay? So we're using heavy timber in conjunction with steel, right, to create a very large spanning space, right? But it's all spanned with these trusses, right, in kind of this very architectural, exposed structural way, Okay? And he's being very smart in how he uses these various trusses. So instead of having a series of inline trusses, one after the next, these are actually three-dimensional trusses, right, that are spanning this. So if we look at one of these pivot points, okay, they're repeated, obviously, right? From that pivot point, we have two pieces of wood that span out to opposing top girders on the roof, right, or beams on the roof. So that's a triangle in that direction, right? This point also comes down and touches to the next span of the truss, right? So we're triangulating in 3 dimensions as opposed to just 2, which is part of why this really works nicely in today where we're dealing with lateral loading and that sort of thing. Okay? Let's see if I can show you a couple other examples. It creates this really nice open floor plan. Okay? Obviously because we have this truss. The nice thing about this is the way they engineered it, all of the things that are in pure tension are steel, right? So we have these very thin, nice cables, and the struts that are in compression are all in wood, right? So it's a nice blending of the two materials. The detailing of these is really spectacular, okay? Partly because we have beams, right, and columns, right, and trusses that are all coming together at odd angles. So you have to deal with how do you resolve those such that they can come together. This is obviously supporting a skylight above, right? So we have a piece of the truss coming together here. We have a very special plate that's designed. It actually fits in. It's inset into the wood itself, right? Which is just a very nice architectural detail. Those of you that are architecture people take note, right, of how nice this is. Okay, it comes together at a pivot point here, which allows it to flex out of plane, which is exactly what we want. This is connected to a point that's over here, right? Notice these two are then connected together. So it's a really complex joint. So it takes a lot of technical knowledge to be able to do something like this, and a lot of fabrication technique to be able to actually build it, right? So we need the computer age to help us out with these sort of things. So again, here's our, notice we can follow through, so it's triangulated in this direction as well as in this direction. Another example there. This is a great shot except for the TV that's up here. It just bugs me, right? Why they need a TV up there, I have no idea. Another example here where we're seeing a whole debating chamber and a series of trusses above. Fast forward even further, right? This was added after the fact. This is the garden lobby to the Scottish Parliament building. Same architect, but a little bit newer. Okay, these openings here, I should do this in the reverse order, so we're going to jump ahead for just a second. This was the architectural rendering, right? The computer rendering of the space. And sometimes it's fun to see what the computer rendering is and then how it actually gets built, right? Same series of trusses here that are working together with the skylight, right? Understanding that this cord at the bottom is in steel, right? And he's playing with the light to some extent because he's shielding this side and leaving this side open so you're getting reflected light. It's really beautifully done, right? Same thing here. It creates a very complex space. Notice we have our concrete columns coming down, okay? So the concrete column is then supporting the trusses themselves there. Another column there. He's playing with the forms of the concrete also, right? Which is why you get this little spiral that goes up. Just really, really nicely done. This would not pass American codes because it's not small enough railings, but okay, whatever. If you're outside the country, you can get away with stuff like that. Sometimes it's fun to see the construction. I know this is blurry, but it's good because you can kind of see what it looks like from the outside. So you've got these spines, right, with all of the structural support here. It has no roofing on it just yet, so you can see all the scaffolding underneath and the cranes trying to actually build this particular building. And again, there's the rendering. So you can tell that I think we were looking at this one here and that one there because those are the ones with the skins on them. This one's exposed completely. But you get the idea of what he was going for, and the rendering matches what was actually built. Okay, so we're jumping again back to the U.S. You guys saw some of these at the beginning of the class, but now that we've lectured on heavy timber construction, maybe this will help things sink in a little bit. This is Bolin, Sawinski, Jackson. This is the Ledge House in 1992 through 1996. Okay, and the really nice thing that they're dealing with here is we have our very standard girder, we have our very standard column, but they kick the columns and the girders off axis, and they're using those both as lateral braces, right, and as the primary structure of the building itself, right? So they're messing with how they're using it. So when you really understand something like this, you can get away with doing things like this, where you have these kicked off axes. I have a better example over here, right, where these this grouping of columns, these heavy timber columns, is supporting the roof, but it's also serving as the lateral bracing for that particular corner. So they're serving a dual function, which is really nice. The detailing that they do is really spectacular. And that's part of why I like to show these in terms of how all these steel brackets come together. They meet this nice concrete plate that's isolated from the rest of the floor. Just really nice detailing. Okay, this is completely heavy timber, right? Because we come up here, we don't have sheetrock, right? So they're relying on the fire resistance of the heavy timber to do their building. Really nice that they have all this rock inside the house too. So it's just cool, right? We talked about this at the very beginning. Okay, this is one of their details. Notice all the ends of the beams are rotting, right? So this is the fact that I'm reminding you that this is wood, and it is, if it's exposed to moisture, it is going to rot. That's why we have this funky little cap on this. So not everything's perfect. They're a good firm, but they make mistakes. Okay, we talked about Bill Gates' pool house a little bit. You guys remember these slides, right? Again, I just want to point out how nice their detailing is, right? So we're in the heavy timber realm, but we need these steel plates to connect the column to the ground, handle the lateral loading, right? So they've done this very fancy bracket in steel. They've kept that little gap underneath so we don't get water wicking up because it's in a pool environment. There's going to be water there. It's really, really well done and well executed. So if you understand the principles, you can apply the principles to an architectural design and really use those to your advantage. Yeah.
Instead of having that gap, couldn't you also use like a 6-inch cap? Remember that? Would that work?
Like a steel cap or something? Yeah, certainly. To me, if you're actually looking at the nature of the detail itself, this is a really elegant solution as opposed to covering the bottom of the steel with a cap. Either way is perfectly acceptable. It just has to start to be, are you designing the connection or are you using a prefabricated connection, right? So we can all go out to Simpson and buy, when you go to Home Depot, you buy the Simpson strong ties and that sort of thing. And you can use one of those, or you can do this where you're actually designing the connection because you understand how this works. Okay, and that's what really good architects do. Okay, another example here. This is just a really nice set of stairs, and I just like it, so I'm showing it to you anyway because it's nice. So whatever, right? This is a good example of a hidden steel plate. Okay, so we talked about hiding those steel plates. We're not seeing it on the outside. The bolts are coming through, but we know that there has to be steel in there, right? Because we only have these 6 bolts, and so there has to be something that connects it together. So the same thing has happening here. We have those notches that are cut out. We put the steel plate in and we bolt through. Just good contrast of concrete or stone and the heavy timber. Again, I like it, so I'm showing it to you. Right, this happens. Same thing here with the detail where we have the steel plates that are hidden inside this particular piece. More of the same. Okay, another example. This is in Redmond, Washington. Notice a lot of this architecture is kind of cabin-esque, Tahoe-esque sort of thing. That tends to be where we see this. So if you're not interested in this kind of architecture, this might not be the building method you would choose, right? Very same concept that was introduced in the Sea Ranch studies, right? Fast forward to today, very open concept, very few walls in this house, a lot of glass. Not particularly energy efficient, right? But we have this series of columns, this series of heavy timber that's allowing that very open floor plan to exist, okay? Again, they've done a very nice thing with the columns because they understand how to manage the lateral loading. So we have a column that's connected at the bottom here, but that slightly tapers to come out, right, on either side. So it's an elegant way of handling that kind of lateral loading. We're splitting the column in that context. They use some steel in conjunction, so it's kind of a hybrid. That's obviously the kitchen. All of this comes up to the central vault, right? Here's our kitchen. There's our vault above. It's a pretty cool space to cook in. I wouldn't mind if this was my kitchen. That would be just fine with me, right? I probably wouldn't be here teaching you, but I would like it nonetheless. So again, we have these columns that have that nice taper to them, right? So it's very well resolved because the architect understands the nature of how the building has to be built. Okay, and that's the key thing that I want you to take away with this. Notice again that this is all heavy timber construction. We have our decking, right, or our planking. So we're relying on all of that. We're not a hybrid construction in this either. This is looking straight up, right, at that opening. Yeah.
I see there's different color, wood or timber.
These.
Is it different?
I'm not
types of
sure. I've
timber,
never been there.
or-
Some of this may be steel. And I'm not sure whether they're using different lumber or they're actually using steel in here in
No.
conjunction with it. I'm not sure because I haven't been there.
In timber construction, would you use paint? Would you use a different type of varnish or kind of?
You could. That kind of stuff is open for whatever the architect decides they want. Okay? I wouldn't be surprised in here, given the structure, if this was wood that was stained differently to accent it.
Or would you combine different types of wood?
You
and
can.
stuff like this?
Absolutely, you can. So, as long as it's within the same realm of wood, you're fine. And this is the bathroom, just because. You know, there's no heavy timber in here, but it's kind of a cool bathroom, so I'm showing it to you. Anyway.